Welcome to Module 3, Unit 11. This unit introduces agricultural waste management within the broader debate on sustainable food system and climate change mitigation. Agriculture is not only a provider of food, but also a major user of natural resources, and therefore a critical sector in the pursuit of sustainability. In recent decades, the intensification of production has significantly boosted yields, but this has also generated a considerable increase in residues, byproducts, and waste. If not properly managed, these flows can compromise water quality, accelerate soil degradation, and contribute to global greenhouse gas emissions. At the same time, waste is not merely an inevitable byproduct of food system. It can be reframed as a potential resource. Through strategies of circular economy and bioeconomy, what was once considered a liability can become a driver of innovation and sustainability. This duality, waste as both a problem and an opportunity, forms the conceptual basis of this lesson. Agriculture is one of the foundational pillars of societies. It secures food supply, supports rural economies, and sustains millions of livelihoods. However, the sector operates under growing constraints. First, demographic expansion, with the world's population projected to reach nearly 10 billion by the end of the century, demand for food will increase dramatically. This will require either expanding agricultural land, which is environmentally costly, or improving yields on existing land. Second, environmental sustainability. Agriculture is a significant driver of biodiversity loss, soil erosions, and freshwater depletion. Current production patterns are not fully aligned with the need to maintain planetary boundaries. For instance, nutrient runoff from fertilizers contributes to eutrophications, creating dead zones in aquatic systems. Third, agriculture is both contributor to and victim of climate change. It contributes through greenhouse gases emissions and land use changes, and it suffers to extreme weather, shifting rainfall patterns, and rising temperatures. These tensions makes waste management more critical. It is one of the levers to reduce agriculture's environmental footprint while strengthening resilience. Land is among the most contested resources in the modern era. Currently, about 50% of Earth's habitable land is dedicated to agriculture. Within this, livestock farming dominates. Pastures and cropland for animal feed together account for three-quarters of agricultural land. Yet, despite this enormous spatial footprint, livestock contributes only 18% of global caloric intake. This discrepancy points to inefficiency in resource allocation. Producing animal protein is inherently more resource intensive than growing crops for direct human consumption. The growing demand for meat and dairy in emerging economies will likely exacerbate this imbalance. Moreover, competition for land is intensifying in regions like sub-Saharan Africa and Southeast Asia, where urbanization and population growth accelerate land use conflicts. Adding to this, land degradation processes such as desertification and soil salinization further reduce the availability of fertile land. As a result, more attention must be given to sustainable intensification, agroecological approaches, and land governance frameworks that can ensure efficiency without jeopardizing ecosystem. The agricultural sector is deeply entangled with the global climate system. Food systems account for roughly 30-33% of anthropogenic greenhouse gas emissions. Livestock and fisheries alone generate around 31% of food-related emissions. Methane emissions from ruminant digestion, known as enteric fermentation, are particularly significant because methane is 28-34 times more potent than carbon dioxide over a 100-year timescale. Cropping system at another 27% with nitrous oxide released from fertilizer use and manure being especially concerning as it has nearly 300 times the global warming potential of carbon dioxide. Land use changes, especially deforestation, and the drainage of carbon-rich soils contribute an additional 24%. Beyond the farm gate, supply chain, from processing to transport and retail, account for 18%. An often overlooked fact is that food waste alone contributes nearly to 10% of global emissions of greenhouse gases. Every ton of food discarded represents wasted water, lands, energy, and labor, along with unnecessary emissions. Thus, addressing food system emissions require both technological innovation in farming and systemic changes in consumption, diet, and waste reduction. Agriculture generates about 1.3 billion tons of waste annually, projected to reach 3.54 billion tons by 2050. This includes crop residues, livestock manure, post-harvest losses, and agro-industrial byproducts. The environmental risks of mismanagement are substantial. Nutrient leaching pollutes groundwater, organic matter decomposition releases methane and nitrous oxide, and poorly handled manure can harbor pathogens affecting both ecosystems and public health. But the challenge is not merely technical, it is also socioeconomic. Many farmers lack infrastructure to store or process waste, and awareness of its potential value remains limited. For example, while manure can be a valuable organic fertilizer, in excess it becomes a pollutant. Similarly, crop residues may be burned in the field for convenience, releasing particulates and greenhouse gases. A paradigm shift is required. Waste must be recognized as a resource within the bioeconomy. Valorization pathway can turn residues into products with both environmental and market value, but this requires policy support, farmer education, and investment in technologies. Waste management can serve as a mitigation strategy for agriculture's environmental footprint. Several approaches stand out. Composting, because converting organic residues into nutrient-rich soil amendments can improve soil fertility and structure. Anaerobic digesters. These can produce biogas, which can replace fossil fuels, and digestate, which can be applied to field as a biofertilizer, or using bioenergy and biofuels, producing biodiesel, bioethanol, or biohydrogen from waste streams reduce the reliance of non-renewable energy sources. Or also with bio-based materials, developing bioplastics, industrial enzymes, organic acids, and functional foods from residues. From a policy perspective, frameworks like the EU Common Agricultural Policy and the European Green Deal increasingly emphasize circularity and resource efficiency. These initiatives not only aim to reduce emissions, but also to create economic incentives for waste valorization. In practice, adopting these strategies can reduce environmental impacts, generating additional income for farmers and contributing to the global transition toward a circular economy. This unit aims to build both knowledge and critical thinking. Students should gain a comprehensive understanding of the environmental impacts of agriculture, including greenhouse gas emissions, land use, and pollution. They learn to identify and classify different types of agricultural waste, evaluate their risk, and understand how waste connects to broader sustainability agendas, such as the Sustainable Developmental Goals. Beyond technical aspects, students will also explore regulatory frameworks, particularly within Europe, which shape waste management practices. They will examine technologies from traditional composting to emerging nanotechnologies for waste valorization. The ultimate goal is to encourage system thinking, to see waste management not in isolation, but as part of a broader social ecological system where environmental, economic, and social dimension intersect. In conclusion, agricultural waste management is both a challenge and opportunity, with food demand increasing and environmental boundaries tightening. The way we handle waste will shape the future sustainability of agriculture. Properly managed waste can reduce pollution, mitigate climate change, and generate valuable resources. Mismanaged, it amplifies environmental degradation and squanders potential. The path forwards require a cultural and systemic shift. Farmers, policymakers, scientists, and consumers must collaborate to move from linear take, make, dispose models toward circular, regenerative systems. Only then can agriculture continue to meet human needs while respecting planetary limits.